So Unit 3 is really about electrostatics, and then Unit 4 is about electric circuits, and then Unit 5 is about really about electricity and magnetism. So really this whole series of 3, 4, 5 is all about electricity in some form or fashion. And since y'all didn't get pretty much any electricity and physics last year, this might be some of y'all's first exposure. Now, if you've taken an electronics course, that's good. Most of the stuff that we learn is actually stuff you should learn before taking an electronics course. So, oddly enough, your electronics knowledge is probably higher than what we're going to get to in here, but we're going to have to work our way up to that, because we're going to get a lot more detail. So, starting off, we have electrostatics and charge. So, what's electrostatics? Well, it's pretty obvious. It's the study of static electricity. So electricity is specifically talking about charges, and in our atoms, what parts of the atom are charged? Electrons and protons. What kind of charge does an electron have? Proton has, neutron has, neutral. We know these things. So static electricity, static means stationary, okay? Unchanging, static. So static electricity means it's unchanging. And that's what's interesting, is because typically when we talk about static electricity, we end up talking about, lightning and, you rub your feet across the carpet or something, you shock yourself and touch the doorknob. That's static electricity, but really we only notice it when it moves, okay? Sometimes we'll notice it when it's stationary, and we'll talk about that, but essentially these things are static because most of the time, like 99% of the time, the charges aren't moving, okay? Occasionally they will discharge, that's what we see as a little spark or a lightning bolt, but most of the time it's static, it's stationary. And when that's static like that, that's when we're going to look at our calculations. Like electricity flowing is called current, or current electricity, which is more of our next unit. So yeah, the main difference here is that with static electricity, you're not going to be plugging your hair dryer to it, right? That's current. We will get there, but right now we're going to talk about static electricity and what happens, because it turns out one of the very key components to an electric circuit actually uses static electricity constantly, basically. So, what's a charge? Well, we kind of already know this, right? The biggest thing I want to point out here is not positive and negative charges. You guys know that for years. It's here that we say something is charged when it has an unequal amount of positive / negative charges. Because a lot of times you say, oh, that's positively charged, that's negatively charged. But I want you to take a second and think about the logical thing that's going on here, is that everything, this desk, chair, wall, you, whatever, you guys all have atoms, you guys all have charges. Overall, what is your charge most of the time? Neutral. So the trick question is, how many negative charges do you have? Well, the answer is you have just as many negative charges as positive charges. You don't know how many it is, but they're equal. And so when we say something is charged, essentially what's happened is either you gained electrons or you lose electrons. So typically when it comes to electricity, we look at just the flow of electrons, although, it will be noted, there are actual working electric circuits where only positive charge flows, okay? Most notably, in a circuit like that that's actually in production is actually on your hydrogen fuel cell vehicles. So for those of you who don't know, like we have gasoline powered cars, cool. And everybody talks about electric cars, which are cool. Matter of fact, I think McLaren just came out with a new electric car, has just 2,000 horsepower. It has, basically 500 horsepower per wheel. That's pretty neat, but I find it really remiss because everybody just skips over the hydrogen fuel cell cars. And that's kind of understandable here in Texas, because for some reason Texas likes to be very odd about things. For instance, you might notice that Texas leads the nation in wind power. That's because there were people down in Austin that actively campaigned against solar power. They were like, no, we don't want solar power, and so like, they actually made it for years, it was very difficult to get anything, like even solar panels on your house. So you'll notice that even though we have West Texas, where basically nothing is, we don't have giant solar farms in with a big desert that we have. I mean, it's not technically a desert, but it's pretty close. Well, we got some wind turbines. So, and I'm not saying there's anything bad about the turbines. If you've ever been up to the Panhandle, there's a bunch. And one of the reasons most people don't realize is, you know, we're kind of, that area is in the plains, but there's actually a small ridge there. And so it's kind of, you kind of drive up to like the Amarillo area and then back down when you're going into the plains. So it's kind of a ridge there, so it actually makes a pretty good place for wind turbines. But I just think it's funny to be like, yeah, well, Texas has the most wind turbines because we refuse to build solar panels. That's a weird choice. But my point being here is when you're looking at these different things, we simply say something is charged because it has a bit more positive or negative. And so in terms of the hydrogen fuel cell vehicles, like California, all of their public transportation runs off of hydrogen. And so essentially it looks just like a gasoline-powered vehicle. Like you drive to the station, you plug in a hose, you fill it up with, in this case, hydrogen gas. And I always think it's funny because students are like, but doesn't hydrogen explode? It's like, yes, it does explode. So does gasoline. That is the definition of what gasoline does in your car. It explodes. It's an internal combustion engine. Anyway, that aside, hydrogen, the way hydrogen fuel cell vehicles work is they use hydrogen, which molecular hydrogen is just H2, and it's pressurized, and most cars that you can buy only have like a 5-gallon tank. And that's because what they do is they take the hydrogen out and they separate the electron from the protons. They actually make the protons run through the circuit. And when they come out the other end, they just recombine with the electrons and they get released out the back. And they very quickly usually combine with oxygen to form water. So the only thing that comes out of the back tailpipe of a hydrogen fuel cell vehicle is water vapor. So that's pretty cool. But what's interesting is that the hydrogen fuel costs a lot more than gasoline, especially nowadays. It's like $5, $6, $7 per gallon. But, like I think the Toyota, what is it called? Both Toyota and Honda have production vehicles that you can buy in California that run off of hydrogen. And most of them get like 60, 70 miles per gallon. So it's like, yeah, the hydrogen costs more, but it also is way more efficient. And that's the beginning efficiency, because most of them are 60 to 70% efficient. Whereas if you look at gasoline powered, you know, if your car gets like 30 miles per gallon, you're like, oh, that's pretty good. That's after like 100 years of development. You got them up to 30 miles per gallon. So I agree that, you know, gasoline powered cars need to go away. But again, the reason why you don't see hydrogen powered cars around here is because the last time I checked, the closest hydrogen fueling station to DFW was in Albuquerque, New Mexico. So, but it's kind of like a chicken and egg scenario. Like, are you going to buy a hydrogen powered car if you ain't got a gas station? Well, no. But who's going to build a gas station? Nobody going to buy any hydrogen fuel gas. But see, that's what happened in California is that the state just decided they were switching everything to hydrogen. And since they knew they were going to have hydrogen cars, they built hydrogen stations. So it just kind of happened out there. But you got to think about it. All right. So again, with the charges, we already know opposites attract, likes repel, right? I don't think anybody's surprised by this. Right? So most of the stuff is very basic stuff, and really, this is what you would have learned last year in Physics 1, but there's really nothing else here. We will get way more in depth. So again, typically only electrons move around. I did take that time to tell you about hydrogen. But why is it that the electrons move? Well, it's just like heat. We already learned about thermodynamics. Electrons flow from high concentration to low concentration. And the reason why electrons flow is conductor of electricity and a poor conductor of heat. It's also a poor conductor of electricity. It's for the same reason. So, I can't remember if I pointed this out before, but if you look at the periodic table, you guys hopefully learned in your chemistry class a little bit about that. And you learned about a couple of different bonds, right? What are some chemical bonds you know? Ionic, covalent, metallic, polar. Maybe like a hydrogen bond. But if we focus on the big ones, we got ionic and covalent. That's what most people spend their time studying, at least in high school. So an ionic bond, can y'all tell me what kind of things make an ionic bond? Metal and non-metal, right? So metals on one end of the periodic table, non-metals on the other. Okay, boom, we get ourselves an ionic bond. We're not going into details. What about that covalent bond I mentioned? Covalent is two non-metals, like oxygen, O2. That's covalent bond, right? So then you also mentioned metallic bonds, which are what? Only metals. So that's what makes them good conductors, is most metals are good conductors because they make metallic bonds. And the reason why most people don't, especially in high school, don't really study metallic bonds is because they're complicated. Because an ionic bond makes sense. Because you're like, okay, hydrogen, let's do salt, okay, NaCl, right? So Na has a positive charge because it lost an electron, and you could say, okay, well then chlorine picked up an extra electron, so it has a -1 charge, and they're attracted, makes sense. We get table salt. Okay, that's ionic bond. A covalent bond is where the two nonmetals are sharing some electrons. So you think about like oxygen, O2, it's usually, oxygen has 6 electrons normally, another oxygen has 6. And so you say, okay, well in the covalent bond, the first oxygen is going to share 2 of its electrons, and the second oxygen is going to share 2 of its electrons. And so you have these 2 covalent bonds, right? Where they're each sharing 2 electrons. That's not too bad. But the metallic bonds, if they're even mentioned in your class, it's just like, yeah, it's kind of like covalent, and then you just kind of move on. Because it's really complex, because it turns out the metallic bond, like if you have, it's like aluminum bonded with some more aluminum. It's not just this aluminum atom is bonded with the one next to it. It's bonded with all of them. Because it's kind of like I like to think of it like a covalent bond on steroids. But like every atom in the metal is sharing its electrons, not just with the atom next to it, it's sharing all of its valence electrons with every other atom in the metal. And so that's what makes it complex because, metals don't have just like 2 or 3 atoms, right? They got trillions. And so that's what makes them good conductors of electricity and heat, because when you think about it, a good analogy that's usually used is think about it like a pipe full of water. Okay, if I have a pipe, let's say upturned at both ends, I can fill it completely full of water, then both ends is bulging up with water on each side, right? That's kind of what you think of a wire, like a copper wire as, is it's just full of electrons. And it turns out that if I put one more molecule of water into this side of the pipe, it will push another molecule of water out that side of the pipe. Does that make sense? It's completely full. And so the same thing happens with electricity in your wire, that if you put one electron in over here, it will push out an electron over the other end. Now, are those the same electrons going in and out? No. But that's the key when it comes to like electric circuits and stuff, is that they're not building up this big static charge like we're going to talk about here. But that's what's happening, is that the electrons or heat want to move from an area where they're all stuck together, and they want to get apart, right? Because all the negative charges repel against each other. So what happens if a positive charged object touches a negatively charged object? A positive object and a negative object touch it. Shot. Okay, but what's physically happening on that shot? What is the shot? Electrons are moving from where to where? From high concentration to low concentration. So which one has a high concentration of electrons? Negative pi. So that's physically what's happening. The electrons are moving from the negative end to the positive, right? Right? And it says right here, the electrons will flow until they're at the same potential. Now we have no idea what potential is. Potential is voltage. Okay? They will flow until they're at the same voltage. Now, I say this because a lot of people say, well, they'll flow until they're both at 0. No. Maybe they end up at 0. But they will flow until they're at the same potential. Does So essentially, if you had something that was like, you know, negative 10 volts and negative, positive 2, well, what's 10, negative 10 plus 2? Negative 8. So they're going to end up at negative 8. They're not going to end up at 0. Does that make sense? Like that's not how it works. It could end up at 0, but that would just be coincidence. How many electrons does something have if it's neutral? And that's right. So this is a comic strip from XKCD. It's good comic strip. So fun fact about this, when I was growing up, I had this old pickup truck, and my buddy's dad was a mechanic. And one day I was over there and he asked me, he's like, when's the last time you tuned up your truck? I was like, what does that mean? And he's like, you know, replace like the spark plugs and all this stuff. I'm like, huh? So he made me go out and buy like all the stuff, and I had to replace like the distributor cap and rotor and the spark plug and all this stuff. And, you know, he helped me put it all in. When I got done, he's like, okay, start up, drive around the block to see how much better it runs. So got my truck, started up, drove around the block. It didn't seem like it did any better. And so I came back, and he was like, oh, it runs a lot better. I'm like, not really. And he's just like, oh, what are you talking about? He gets in my truck, and he drives around the block, and comes back, and he's like, yeah, you're right, that's not very good. And so he starts like poking at it, because he's trying to figure out what's wrong with it. I have no idea what's going on, so I just go inside, and I start getting a drink. So me and my buddy are inside, and we can hear his dad start screaming outside, like something has hurt him. And so we come back out, and we're like, hey, what's happening? He's like, okay. He's got like my truck running. He's like, okay, go ahead and put your hand right here. I'm like, okay. I just put my hand like on the grill at the front of the truck. And he's like, now touch over here. I'm like, no. He's like, no, you got to touch right there. I'm like, nah. I don't know what's going on, but I'm not going to touch that. And he's just like, come on. I got to figure out if it happens every time. And I'm like, so then he tries to get his son to do it, and his son's just like, nope. He's like 5 feet away. The dad gets all mad, and he touches it, and he goes and he touches the cap, and I can see a visible spark jump out of the top of the engine. And he was a little upset. And it turns out that cap that I bought for the engine, that's actually the physical part, it's called a cap. It turns out it was defective, because sparks should not come through the cap. Because essentially the cap helps distribute the spark to the actual spark plugs. And it turns out I just had a defective cap. But he had to know if it happened every time, because if it happens every time, that means that part is defective, because I just bought it. So, you know, you gotta make sure it happens every time. Otherwise, it may have just been a fluke. I was not willing to accept. Turns out you can do the same thing just with a piece of metal, but you didn't have to actually put your hand in it. All right, so now we have the term ground. And so I'm sure you've heard of this a lot, like what does this mean? Now, physically, what ground means is it's a large body, usually a very huge body of just potential, a sea, a reservoir of charge. A lot of times we use physically the earth as the ground because it's a large body of extra charge. So a lot of times somebody says, is that grounded or should this be grounded? You can literally think of it being connected to the physical earth. And I'm not just saying that like, oh, you can think of it like that. We have outlets in this classroom and at your home, right? How many holes makes up one outlet? 30, right? And usually most outlets have at least 2 sets of holes, but 3. Have you ever noticed that some things you plug in have 3 prongs and some only have 2? Did you notice that they both seem to work just fine? You ever gotten something that had 2 prongs and then you bought new one and it had 3 and you're like, well, my old one didn't have 3, why does this one? Well, truth be told, if you don't know this, you've got 3 outlets, and in this country they're shaped like that. In other countries they're shaped differently. Mostly at first just because it was just random happenstance, but nowadays, these outlets are regulated by the government, so in this country, all of these outlets are the same shape and size, so you can plug in any charger there, sizes because they don't want you to plug your charger into it. Because how much voltage comes out of this wall outlet? Well, in this country, it's around 120 volts. So somewhere between 110 and 120 volts, depending on how much power comes in light. If you went across the sea to say, Europe, their outlets put out 220. Because that's what they decide on. They do 220 at 50 hertz, we do 120 at 60 hertz. Hertz is the frequency of cycles per second. We'll get more detail on that. But what I'm saying is a lot of people get upset, like, especially stupid Americans, they go across the sea and they're like, why doesn't my outlet work over here? It's like, very specifically, they don't want you to plug it in, which is why it doesn't work. Now, nowadays, most chargers are pretty smart. They can handle the difference in voltage. You just have to tell them how to do that. But that's really just the two little slips in the outlet, right? That's where you're getting your power from. You can think of them as like one side positive, one side negative. Really, they're both kind of positive. But we'll talk about that later. What I'm talking about right now is that third hole, that sort of roundish one. That one is the ground. Now, the two slender ones, the little rectangular holes, those two are where you're getting your power from. And so when you think about making a circuit, you can think about like one side, the power is coming out, let's say that's the positive side, it runs through your little circuit, makes a circle, goes back to the negative side, that's how it works. But that ground one there is just for grounding. So literally the two like rectangular holes are connected to the power lines that are running into your house or into the building. But the third one, that round one, all of those are connected together. Like literally, they are connected together. All those round ones are connected together, and they're usually connected to a piece of metal that is buried in the ground underneath the school or next to your house. What's interesting is that nowadays they make them differently, but like older homes, especially like the homes that I grew up in that were built like back in the 60s, they actually, you could see the grounding rod out, like it was just buried in the ground next to the house. And like growing up, I was like, what is this? And like my parents didn't know what it was, and you'd be familiar with it. It's not harmful, it's designed to be electrically neutral, okay? Because the whole point is that if you're using, let's say, a computer, and it builds up some static charge, if you touch it, it will shock you. Does that make sense? If you build up static charge and you touch your computer, it will shock you. But the whole point is like, not on laptops, I'm talking about on actual desktop computers, those have three prongs, because the whole point is if you have like an electrical short in your computer, it's electricity starts, discharging randomly for some unknown reason, the amount of electricity that runs through your computer is way beyond what's needed to kill you. Speaking of how much electricity is needed to kill you, the lowest voltage I know that has actually killed somebody is not 120 volts, it's actually just 9. And that's a big mistake when it comes to electricity, is people think, oh, 100,000 volts, that's going to kill me. No. What kills you is how quickly you change voltages, how much current runs through you. That's what kills you. Because saying 100,000 volts kills you is like saying being 100,000 feet in the air kills you. No. You can be in a plane and be perfectly fine. However, if you decide to just step out of that plane and go down very quickly, that would probably kill you. So 100,000 volts by itself doesn't typically kill you, but going from 100,000 to 0, it tends to end poorly. So higher voltages you should have a respect for, just like higher elevations. Just try not to fall down the cliff. But again, anything that can be grounded as long as it's big enough compared to the object. What's interesting is that for some of the things that we'll do in this class, you can serve as a ground for it. For instance, one of your projects that are going to be coming up a little later, it's actually in the next unit, you actually have to build some things, and you're large enough compared to the stuff that you're building that you can act as a ground, which means you can totally electrically discharge everything that you're doing and not even be aware that you did anything. I had a lot of students get upset last year because they didn't understand they were just completely discharging it when they were touching it. It's like, yeah, there's nothing happening because you took all the charge. But most people think, oh, when it discharges, it has to spark. Sparks can happen, but only in very specific situations. But basically, if you touch an object, you can ground it. Now, things that have a lot of charge, if you quote unquote ground it, you'll notice that extra charge, right? So whenever you ground something, it kind of depends on how much charge is flowing. Like I said, you can serve as a ground for relatively low amounts of charge, but in the end, we generally use Earth as ground. Fun fact, Earth actually has more electrons than protons. We know that because the Earth has an electric field. And some of it leaks off into space, and some of it comes back from space, but overall, the amount that comes in keeps us negative. I can tell you, I forget how much it might even be in these notes, like the Earth has an actual negative charge, and it's massive. You're like, man, that's a lot. But then when you spread it out over like the surface of the Earth, it's basically nothing. Because the Earth's kind of big. What happens if a negatively charged object is grounded? Yeah. The electrons flow from the negatively charged object into the ground until, again, they're both at the same potential. In this case, the Earth is, again, really pretty dang big, and so we tend to say it's neutral. And so, you know, if you add 10 trillion electrons to the Earth, what happens if a positively charged object is grounded? Yeah, electrons flow from the ground to the object, so they're both the same potential. All right, so charge. How do we get charge? Because everything has these charges. So the big key here is charge is never created nor destroyed. Charge is simply separate. We know things already have positive and negative charge, so to make something charged, we simply separate the charge that's already on the object. So the three ways that we do that are friction, conduction, and induction. Friction is very simple, and it's the most common way to charge an object. You just rub two things together. Now you might notice that if you just rub stuff together, does everything just get a charge? No. So if you really want something to get a charge, you got to be a little bit more specific. But generally, one object rubbing against another one can produce a charge. So here I show you a picture of some socks. And the reason for that is most of you have, done laundry, hopefully. But most of you might notice that if you don't put like a dryer sheet in there, like your socks seem to stick to everything. That's because the socks are typically like wool or cotton, and they'll roll around in the dryer, and they'll transfer some charge to another object. And because one is positive and one is negative, now they're attracted to each other. And so friction, just two objects rubbing against each other, can cause them to be charged. And that happens because typically, like I said, one wants to be charged, one wants to be positive more than the other. Just like your ionic bonds, that some atoms, like to steal charges. Like oxygen likes to steal negative charges. And so, like some of you, especially if you have long hair and you've been like brushing your hair or combing it, you'll notice that especially in the wintertime, you get some static charge, right? And it's interesting because if you have long hair and you brush it a lot, then you realize like it's getting worse because you're building up charge, right? Like your hair might be building up a positive charge and combs building up a negative charge, and yeah, it's frustrating sometimes. But friction. And the important thing here is that it's not really the friction, it's not really the rubbing that's transferring the charge, it's simply taking the objects and pushing them together. But again, more surface area allows more charge to transfer, and so you can generally get more surface area by rubbing it. So I just want to emphasize that it's not really the physical act of rubbing that transfers the charge, it's simply the one atom wants electrons more than the other. And so the more atoms you have, quote unquote, touching, they're not really ever touching, but the closer they get, the easier it is to transfer the charge. So that's friction. Number two, conduction. That is where two objects directly touch. And so this is typical that you already have a charged object, and you touch it to a second one, and you get the object to transfer charge. Like I said, sometimes you'll see a physical spark, sometimes it'll just transfer the charge without any visible thing to be noticed. But that is a way to transfer charge. So if you simply have something that's charged, like if you rub your feet across the floor and you know that you've got a static charge, you go over to your friend, you touch them, you shock them, well, you charge them by conduction, right? Now what's interesting is that what a lot of people don't realize is that if you do that, if you shock them, what's funny is that like the person that gets shocked like tries to go like rub their feet and go shock the other person. When two people have been shocked, they're at the same potential. It might be zero, but chances are both of you are still slightly charged. You can actually go shock other people, but it's probably not going to work if you're trying to shock each other because you have the same potential. And it should also be noted that when you get shocked, pain is one of those things that it's ineffable, and it's hard for us to communicate how much pain you're actually feeling. And good doctors know this, which is why you have those stupid scales. If you've ever gone to the doctor in pain, they're like, oh, on a scale of 1 to 10, how much pain are you in? It sounds really stupid, but when you take a step back and think about it, like it's really basically impossible to describe how much pain you're in. And so they just say on a scale of 1 to 10, and you go, okay, it's a 1 or 10 or whatever. It sounds stupid, but really it's the only thing that the doctors have to go on. It's ineffable, and they can't tell how much pain you're in, because it turns out, you know, like say you're getting shocked, okay, well, there's action-reaction, right? If I touch you, you shock me, I shock you, right? We both get shocked. But chances are one person thinks it hurts more than the other. And a lot of people are like, ah, you're just a wuss, you know, suck it up. It turns out that's not really the case most of the time. It turns out that your physical nerves will act differently than somebody else's. And it turns out for electricity, a real big factor in what you feel is actually how hydrated you are. Like, the more hydrated you are, the more you feel it. The less hydrated you are, the less you feel it. So the more dehydrated. But I want to bring that up because some of you will definitely be getting shocked in the days to come. But I always think it's interesting when we do this, because people are always like, oh, you're a wuss. And I'm like, I want to emphasize that now, that like, if somebody says it hurts, like real bad, like you have to believe them. Because you're not in their body. You don't know what it felt like, okay? And for you, it probably does feel different. And like I said, there's a whole, you know, genetics and biology and all that. But that aside, like literally just hydrating or not hydrating can actually change a lot of what you feel. Okay, so that's just conduction. Again, charge transferred by two objects directly touching. Induction is essentially transferring charge from two objects not touching. And induction is a little bit different. I mean, it has the definition here. It says bringing a charged object near a neutral object will induce a charge. I want to go through this real slow here. And the reason why I want to go through real slow is because when you guys get questions on this, on your audit, on quizzes, on tests, on the AP exam itself, you're basically not going to have any questions about friction charging, because that's pretty straightforward. You're not going to have any questions about conduction charging. That's pretty straightforward. If you have questions about charging, they're almost all going to be induction. And like, for example, the AP test, I guarantee you there'll be 2 or 3 questions about just induction and nothing else. Because it can be confusing, all right? Because there's many different ways to charge by induction, just depending on how you start. So I'm going to give you a typical example, and I should note that today we're just going to run through the notes and hopefully get to the lab. But next class I want to get the demos out and show you these things, like physically show you things being inducted. But the problem with physically doing it is you can see the results, but do you see any charges? No, you don't see the charges. You don't see charges typically. So, I think it's better to start with this. So, the way something goes is you have a charged object. So let's say we have a rod, and we did something to get negative charges on it. You all see that? So then, to charge by induction, let's say that we have a couple of spheres here on insulating stands. This is a pretty typical example here. So I've got 2 spheres attached to insulating stands here, and they're touching, all right? And so it should be noted that most of these objects are probably going to be metal. So like, maybe this is a metal-coated sphere, this is a metal-coated sphere, this is like a plastic rod, it's like a plastic stand so that it's insulated from ground. And maybe this is a plastic or metal rod, whatever. So let's say that this is our starting scenario. This has a negative charge, right? These 2 guys are neutral. So to charge by induction, let's say that we want to charge this guy by induction right here. What do? Well, the first thing you do is you bring your negatively charged rod near this object, okay? Don't touch, because if you touch, then we're in conduction, right? So no touch. So these 2 don't touch, but you bring it near. What's going to happen to the charges that are already here? Because everything's made out of charges, right? What are these positive charges going to do? Are they going to be attracted or repelled? Positive or attracted? attracted. However, in a solid object, the positive charges are part of your nucleus and probably don't actually move. Now, in some respects, if the field is large enough, you can get them kind of like leaning towards the positive charge, or towards the negative charge in this case, but they don't really go anywhere. But in some cases, it can be significant. What happens to our negative charges? They're repelled. So the negative charges will start to go away, in this case, as far away as they can, right? But these things were neutral to begin with. So if I have 4 electrons that have gone over there, they've left 4 positive holes over here. Does that make sense? And as I bring this rod closer, well, then that's going to force more electrons to go over here, and it's going to leave more of a positive charge over here. Does that make sense? So simply bringing this rod here will get what polarization happening in this object, right? So I know that they're metal, so that these electrons can freely move, right? Now, if I just took this rod away, what would happen to the electrons of this thing? They would just go back and everything is still neutral, right? So charging by induction, this is step 1. You have a charged object, you bring it near a neutral object. Polarization will occur, all right? Obviously, if you have insulating objects, the electrons can't move over there, but you can still get polarization happening on a molecular level. So for instance, you'll have, like on a molecular level, even though the electrons are just like orbiting, you know, we had a thing here, like we have, let's say a positive, let's say it's hydrogen and like 1 electron here. If I bring a negatively charged object close to this, what will end up happening is the positive charge does move, but the electron will essentially be like its orbit will become like real weird, because it's trying to get away from that guy. But again, if you're an insulator, it can't really go anywhere. But it will cause essentially the atom itself to become polarized, even if it wasn't before. But that's not what we're dealing with right now. So again, if we just take this rod away, it's all done. So now the next step, step 2, is actually going to be physically moving this object over. So I'm going to physically move it. So step 2 is you just slide the thing over using the insulating stand. So now I've still got my same object here, right? Still on the stand. Something like that. And then the third step is to remove this bar, right? I'm just going to mark it out now. If I remove this bar, then the electrons that are essentially over here will kind of redistribute themselves. And these electrons will kind of redistribute themselves, giving this guy what type of charge? Positive, which will be evenly distributed across the surface because it's metal. And this one will have what type of charge? Which will be evenly distributed across the surface. So what's interesting here is a couple of things. First of all, did I ever touch this rod to these guys? No. So that's the first thing. I didn't touch. That's the biggest key of induction. The second key is I didn't create 1 charged object. I created 2. Now the close one ends up being the opposite of what I started with, in this case positive, and the far one ends up being the same. But what's great about induction is that if I charge an object by induction, if I charge it by conduction, I just touch this thing and this thing becomes negative, this thing is lost in electrons. But when you charge by conduction, I physically lost the charge here, right? This thing has less charge. But by induction, I can charge them up like this, and then I can use this charge to do stuff. And then, let's say I get them all neutral again, I can put them back to the same situation they were. Have I used up this charge at all? No, I can actually use this again to recharge these guys. And so, charging by induction is great because I don't actually use my charge. I just gain some more. But I can also make, positive and negative. And so the reason why this thing is going to have so many questions is because I could, like the multiple choice questions you'll get on this would be like, give you the first scenario where you have, 2 stands and an object. If this object is negative, the question could be, okay, object 1, does it become positive, negative, neutral under this situation? And it will give you steps. It will say, okay, step 1, you bring the rod near it. Step 2, you move it apart. Step 3, you pull it away. But they will also write those steps out of order. And if you do them out of order, you don't end up with a charge. And so the question of what's the charge of this thing at the end of these steps can be different depending on the order you do it, but also if this is negative, could this be positive? Yeah, this could be positive, thus changing our results here, okay? But it's the same procedure every time, and I don't think that these questions are hard. I think students miss them because they try to go too fast. If you just take a second and go, okay, this thing's going over here, this going over here, okay, fine, I got it. But again, if you try to go too fast, you're just going to destroy these problems. All right? So I'm warning you right now, there's like 17 different ways to ask the same question and get different answers. All right, does everyone kind of understand induction? So it's charging by induction. So we're charging these objects by induction. We don't know how this object is charged. Okay. And so that's what this whole thing is trying to say here. And we can charge by induction because electricity charges actually can act over a distance, kind of like gravity. Okay, so I'm not going to do these demos right now. Okay, so the SI unit for charge is the coulomb. And it was, Coulomb is named after Charles Coulomb, a French scientist who studied electricity. He certainly wasn't the first to study it. But he's the first to actually quantify the force happening between two charges. Now, this was hundreds of years ago, like in the 1800s, almost 200 years ago or something at this point. Actually, maybe earlier than that. But when he was doing these experiments, did he have nice electronic devices like we have today? Nope. No. And so it turns out that in order for him to study electricity, it basically had to be something that was like making a spark. If you have enough electricity that makes a spark, you have a lot of charge, like a large amount of charge. And it turns out that's what he based his formula on, Coulomb's law, which we'll talk about soon enough. But what's interesting about it is when you look at Coulomb's law, essentially it looks like Newton's law of universal gravitation. You've got the force equals some constant, charge 1, charge 2 over the distance squared. Well, his two charges were typically something in the size of a coulomb on two objects that were like roughly a meter apart. They weren't. But what's really hard to emphasize here is the we're talking in the chat. A coulomb is a large amount of charge. It's a dangerous amount of charge. It is a lot of charge. 1 coulomb of charge, to put it in perspective, do y'all think lightning bolts are dangerous? They're fun. You should play around with them. A typical lightning bolt, on average, has between 5 to 7 coulombs of charge. It could have more, it could have less. So if a lightning bolt could have 1 coulomb of charge, just to kind of put in your mind, like, that's kind of dangerous. So typically, we say that the SI unit for charge is the coulomb, but this is defined in a time back before they even knew what electrons were. You have to understand that people started studying electricity and magnetism and stuff. They didn't know what electrons were. They didn't know what protons were. They were just like, it's stuff happening. And so they just started defining things at scales that we still use today, but they didn't know what these things were. Like the electron wasn't discovered until like 1919, something like that. Like, it's just been over 100 years since we figured out what an electron is. Now, you guys have grown up knowing what an electron is. That's cool. But these guys didn't. And so they had to do very large, dangerous experiments. But what I'm trying to emphasize here is that most of the time, when I give you, I say, oh, I got charges here, they're usually going to have a prefix like nanocoulombs or microcoulombs, maybe millicoulombs. You're probably never going to get a problem where it's just a coulomb of charge, because that's a lot of charge. And I'm not saying that you don't build things today. Like if you have a nice audio system, those things can be pushing coulomb levels of charge quite easily. But again, kind of dangerous. But so here, remember the prefix, milli is times 10 to the third, micro is times 10 to the sixth, nano is times 10 to the ninth, if you don't know that. But again, it's just, levels of charge, because again, we don't typically use that much charge. It turns out we don't need anything nearly that much to do our work. proton. However, to actually calculate, like say, the force of an object, we have to convert it from elementary charge to coulombs. And so one elementary charge is 1.602 times 10 to the negative 19 coulombs. So if you have 1 coulomb of charge, you have roughly 16 quintillion electrons. Not a billion, trillion, quadrillion, a quintillion. You have 16 quintillion electrons if you have 1 coulomb of charge. Like that is just a stupid amount of electrons. And I want to emphasize that you can definitely have circuits that have that. They're not like rare. So if an object has 6.022 times 10 to the 23rd more electrons than protons, what's its net charge? In coulombs. So how would you find this? It's got this many extra electrons. How would you find its charge? Time charge and divide by it. Yeah. So you would multiply the 6.022 times 10 to the 23rd electrons times this many coulombs per electron, right? And that comes out to be 96,472 coulombs. I guess I misspoke. A lightning bolt is only 3 coulombs. That's why I write things down. So that's a lot of electrons, right? That's a dangerous amount of electrons. All right, so then how many electrons are there in 1 microcoulomb? Yeah, it's just that divided by elementary charge. So in 1 microcoulomb, that's 6.24 times 10 to the 12th electrons. That's like 6 trillion electrons in a microcoulomb. So, you know, again, these things are ridiculous because it was defined at a time before they really knew what was going on. And so it had to be kind of a dangerous amount of charge for them to deal with. Now it turns out 1 trillion charges here and there don't really matter that much to you. It just kind of depends on how you see it. All right, so again, static electricity here is a buildup of charge on an object. So most of the time, for it to be static electricity, the charge will not move from one place to another in a constant, sustainable stream. So again, it's stationary for all practical purposes. So here in this picture, this thing is known as a Van de Graaff generator, and it causes charges to build up on the outside of it. You know, it could be positive, could be negative, kind of depends on how you build it up. The one we have, I believe, builds up positive charge, so I'm just going to assume this is building up positive charge. So it's taking electrons away. So if you touch it, it will start to take electrons away from you. Now you might notice when you have a lot of static electricity, like your hair and stuff starts to stand up. And that makes a lot of sense because let's say you're building up a positive charge. We're removing all of these electrons. Well, do the positive charges want to be near each other? No. Can they actually go anywhere? No. But they will repel each other. And so in a place like your hair, if one piece of hair is positively charged and the hair next to it is positively charged, they can actually physically move apart because they're just hair. Which is why if you physically build up a charge, your hair will physically stand up because it's trying to get away from everything else that's positively charged. Because the charges will essentially move as far away as they can. Now it turns out air is actually a very good insulator. That's what happens is the charges are building up on you, but they can't actually jump to something else, which is why, you know, your hair and stuff starts to stand up because it's trying to get away, but it can't go anywhere because the air is, like I said, insulates pretty good, you know. Conductors versus insulators, you should know this basically. Conductors allow electrons to freely move, insulators don't. So I'll give you examples of conductors and insulators. The key for your problems really is that if you have a conductor and you put charge on a conductor, it will automatically move to the entire surface of that conductor and distribute itself so it's completely evenly spaced in terms of its voltage. That will happen for every conductor. So if you get a problem that says, okay, you have a conductor that blah, 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 you need to know that it said conductor for a reason. Or if it says it's metal, you know that's a conductor. The charge is going to evenly distribute itself on the surface. If you have an insulator, the charge is not going to evenly distribute itself. It's going to stay exactly where it's put. Okay? We don't look in this class too much at insulators being charged because they're not going to be even. That's more of a physics C sort of thing, where you can have uneven distributions of charge. But you need calculus really to deal with that. So in this class, we won't typically get too much of that at all. I'm not going to mention that. So again, insulators have tight bonds with their electrons, so they tend to stay. So the key here is that you can still charge an insulator. Like a lot of people are like, oh, it's an insulator, it can't be charged. No, you can charge it. It just doesn't move. It just stays right where you put it. So the electrons in an insulator are tightly bound to the positive nuclei, not free to move. So charging it will leave a patch of molecular ions on the surface, but the electrons are essentially immobile. So again, conductors, the way that they typically say it, it's a sea of valence electrons. Think of it like the water. That, you know, if you push electrons on this side, that wave will, you know, go all the way down through the metal to the other side. And so if you put an electron there, it'll automatically distribute itself to get as far away from all the rest as possible. Yeah. So question 5. Metal spheres 1 and 2 are touching. Both are initially neutral. The charge rod is brought near, then the charge rod is removed. Then the charges are separated. Afterward, the charges on the sphere are what do y'all think? So E. Right. So again, the order matters, right? So it's brought near, then removed. Then they're separate. Well, if it's brought near, they polarize, and then it's removed, so then they're not polarized, so it doesn't matter if it's separate. All right, good. Metal spheres 1 and 2 are touching. Both are initially neutral. The charge rod is brought near, the spheres are separated, and the charge rod is then removed. Afterward, the charges on the sphere are negative, positive. What is that? C? Huh? Like I said, I don't think these questions are hard, but you gotta, you know, make sure you read. Question 7. Identical metal spheres are initially charged as shown. So P has positive 4 nanocoulombs, Q has negative 2 nanocoulombs, and R has negative 1 nanocoulombs. It says spheres P and Q are touched together and then separated. Then spheres Q and R are touched together and then separated. Afterward, the charge on sphere R is, think about that. What do y'all think? So, okay, there's a couple of caveats to this, so let me explain it, then I'll talk about the caveats. So first of all, we have touched P and Q together, so P has 4, Q has 2. So what's 4 minus 2? 2. So the total charge between both of these ends up being 2. However, then you pull them apart. So each one's going to end up with 1, right? And since this one has a positive 1 now, and you set it to the negative 1, well, positive plus negative 1 is 0. So when you pull that apart, 0 divided by 2 is still 0, right? So it's 0. Does that make sense? Yeah. Now, I don't think we're going to get too complicated here, but another key factor is that these spheres are all the same size. Okay? If they had different sizes, then that would change, you know, exactly how much charge each thing gets, because the charge gets distributed on the surface. So essentially, a larger sphere will retain more charge when you touch them together. So I think so, but if that was the case, I would have to tell you, you know, like this one's twice as big as that one. And then you know, okay, well, what's the surface area of a sphere? 4 pi. It's 4 pi r squared, okay? But I'm just saying, like, if that's a factor, it will definitely say this one's twice as big as the other. or if it even wants you to think it's okay. But like, we're not quite there. I just wanted to mention that that is something, like this is really easy because they're all the same size. So if you see a problem, they're all the same size, go, okay, cool, this is going to be relatively easy. Okay, cool, that's the end of the notes. So we're all done with that. So we'll go ahead and turn off the recording here.